he was just asking if I had started grading this first test yet, and I said, well, as far as I know, I haven't gotten any of these tests yet. Now, I haven't checked Blackboard in this class, and I haven't checked my emails since yesterday, um, and I probably didn't get them all checked yesterday, but it seems like every time that I think I'm going to have a chance to start grading, something else comes up. Like yesterday afternoon, I said, hey, I've got a little bit of free time now, let me do. The associate dean called and said, well, the instructions we gave you on, he didn't say this, but this is what it turned out being, on spring thing, what they said on there, be sure you put an instructor's name by every course. They had it written on the thing, be sure you put a name by every course. Well, in the math department, we've lost 2 people since they've hired anyone else, so we're short 2 people, and then I'll be not here in the spring. I'll be here January, but I won't be here past the 1st of February. So I couldn't put my name down there, so I put instructors who could teach the classes that we're doing. They're supposedly, they've had opened up a position, but they haven't set a committee yet, and without setting a committee, we can't hire anybody, okay? So we're in limbo there, and I couldn't put a name down, so I put other instructors giving them extra courses to do. So they came yesterday and said, you got too many people down, have too many classes. I said, well, yes, but it said put a name down. I explained to the dean that's what I was doing. She seemed fine with it. Well, they're not fine with it now. They want you to put staff. So I had to go back in and change spring term schedule again. Okay, I had to take some names off, move others' names around and stuff, and then put staffs in other places. Now, of course, I can't do the changes, which would be easy and simple to do. I have to type out the changes for the administrative assistants to do, because department chairs are untrustworthy to get them right, and they give them to administrative assistants to do, which is fine. That's fine with me, but it's more work for me because I could have just gone in and changed the names, but I had to type out which section, which class, is this, and make sure the administrative assistant knew exactly what to do. So it was more work for me, and I had told them ahead of time that's what I was going to have to do. Oh, yes, that's fine. And then they turned around and said, well, no, we'd rather not have it that way. So there went a good period of time yesterday. I could have been grading. I was doing that. So that's my sad song. Okay, so anyway, any other questions, issues, concerns before we get started on today's class? Okay, I don't hear any, so I'm going to see if I can get the screen share to start with, of course, our whiteboard, because that's all we have in this class, since there are no PowerPoints for this class. So now I've got to move around my materials here. And let me also, while I'm moving these around, say something else. It came to mind because of an email I got this morning, I think it was. Yeah, I'm pretty sure it was. Yeah, it was this morning, because it almost made me late for my first class. I had a few moments. I was going to check emails and maybe print off a couple more tests. And it was an email from a student in my last class, the one that just got over with, saying she wasn't probably going to be there today because her grandmother just died, and the funeral is tomorrow, and she said our house is full and I won't be able to concentrate or set aside any time. I won't be there today. And of course I'm sorry for her, and I expressed this too in the email, on her grandmother's death and that kind of stuff. But it also made me cringe, because the places I've heard about the biggest spread of COVID has typically been around weddings, around funerals, or around other big family get-togethers like that, or not necessarily family and friends. Possibly sometimes even church services that people aren't social distancing, and things like this. I just couldn't help but say, please be careful, be safe, because this is where, and I'll just give this example I couldn't give it in the email, but I'll just tell it to y'all. My home county in Georgia is very rural. I mean, way out in the sticks, okay? And when everybody else, especially people in cities and stuff, were really coming down with this really fast, the rural areas had hardly been touched at all. So Burke County, Georgia's rate was very, very low until 1 week. And in that week, they had just an explosion of cases. And they traced them to one funeral. One funeral. Somebody was there who either didn't realize he was sick or didn't know that's what he or she was sick from, asymptomatic, or had just been exposed and didn't know that they were exposed yet. And anyway, the pastor died, and just numerous people at that funeral came down with COVID. So all their numbers have been so very, very low, and then suddenly went like that. That happens, and it happens. I've heard of bridal gatherings or things like this, and then people getting sick from it. And so please be careful, people. I know these times like that are important times, but you know, the health of the community is also really important, and try to maintain social distancing. I'll give this one other kind of example to it. I have a niece who is a medical doctor, and her husband's also a medical doctor. He's an ENT surgeon, so he is extremely gifted and talented and necessary at his work. And his grandmother or grandfather, I don't remember which, died in South Georgia. This was a few weeks ago, several weeks ago, when it was really, really hot. And of course, he went to go see the family. He didn't take his wife and kids because his wife has pretty severe asthma, and one of the kids does too. So there were some issues there, but he wanted to go see the family. But everyone had gathered there, and he just did not feel like he could go in the house. So he greeted them and talked with them and offered his condolences, but they were all standing around outside because he couldn't go in. And so after a while, someone said, well, do we have to stay out here? And he realized they were all uncomfortable. It was really, really hot. But he couldn't go in because he is essential person at his work. And so he could not risk the exposure. So he said, well, I've got to go back, to the farm anyway. So he left so they could go in the house, and hopefully none of them got sick, but they could have. But he couldn't take it home to his family. He couldn't take it back to his patients. He couldn't be quarantined for 14 days. He would have to be if he got it, but it was just something they didn't want to happen. So it's tough. It's really, really tough. And another example, this was early. This was probably March or April or sometime. One of the people at the college, his mother, who has also been an adjunct instructor for us, she was in the hospital basically dying, but the hospital could not let people come in to see her. And it was tough. It was really, really tough. So he couldn't be there when his mom was on her final days. And the funeral had to be very small and very private as well. So it's really a tough time. But please, folks, it's important to maintain safety. Very important. So, sorry, that's my paid political announcement. Let's move on. Any questions, issues, concerns, problems? And let me ask y'all this too. This came up in my first class. Has anyone had issues or problems or difficulty getting your Pell Grant checks or things like that? Are you asking me if I've heard? I don't know what they're going to do. That seems to be, you just nailed what the problem is. The communication seems to be awful, okay? And what one of the students said, I have a big class first thing in the morning, and that's where it came up. And this one student is just really irate about it, and I can understand that too. Um, but evidently, and this is what one of the other students said, and then someone else said they had heard it too, so I don't know if this is true or not, but I've heard it from more than one source, that when our former president retired and you got a new interim president, one thing they forgot to do was, the president technically signs the checks, but he doesn't really, or she doesn't really. It's all done automatically, okay? It's done computer driven, it's done somehow, but it's not actually, they don't sit down and sign the checks. Well, evidently they had not changed that program. Whatever it generates the checks was still had his signature on it, and I guess somebody said we can't do this because he's no longer president. And then they had to go through and get the new interim president, everything done for her to sign the checks, and this is something that did not cross anyone's mind that that was an issue, and evidently it's become an issue. So what they were saying, that's in the works. But what this one student said, and this is what had her so upset, if they would just tell us something, we would know, but we haven't heard squat. She didn't quite use those words, those are my words. And that sounds like, James, from your question, no, I haven't seen an email about it. I haven't heard anything about it. I had heard early on that there was a banner problem. This new operating system we have wasn't functioning properly, and I heard that was the issue. I knew that we had a meeting canceled and that the administrative staff was working all weekend trying to resolve that issue. I just assumed they got it resolved, but once they got that one resolved, then the other issue came up, and so I don't know. I do not know, but I just wondered if it was just that one student or that if it was widespread. But from your question there, it sounds like it's more widespread than we would hope it would be. Now, I would think the direct deposit could do direct deposit no matter who the president is, but I don't know that for a fact either. I assume that's the case. But anyway, I'm going to try to find out, but I have very little resources to do so. Since I'm not on campus, I can't go to someone's office and ask. I'll try to talk with someone if I can find that out. But I just wanted to check and see if others had had that issue too. It sounds like maybe you have. So I think they're working on it. And by the way, this new president, you'll not find anyone who's more student-centered than she is. She's going to do everything she can to get this resolved as quickly as possible. I can guarantee that. She was on the interview committee that hired me 20 some odd years ago. So she's been here. She knows what she's doing. She's top notch. Okay. We're in Chapter 2, Matrices, Section 2.1, Operations with Matrices, and we're starting today on page 46, looking at partition matrices. Are there any questions before we get started on this? Okay. Well, remember we said a system of equations, okay, can be represented this way. It's sort of a shorthand. This is one place where matrix operations really come in handy. You can express a system of equations by A, which is a coefficient matrix, times X, which is the variable vector, you might say, is equal to B, which is the constant vector. Okay, that's the shorthand by writing all those equations down. Very concise. Of course, here, A represents the coefficient matrix. This is where it takes a long time. That coefficient matrix is A sub 1, 1, A sub 1, 2, A sub 1, 3, all the way up to and including A sub 1, n. Yeah, they're still using n. A sub 2, 1, A sub 2, 2, A sub 2, 3, and dot, dot, dot all the way up to a sub 2n, and then a sub 3,1, a sub 3,2, a sub 3,3, dot 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 up to a sub 3n, and then we'll dot 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 this down to a sub m1, dot 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 this down to a sub m2, and dot 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 this down to a sub m. Goodness, this drives me nuts. A sub m3, and we'll dot 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 this over to a sub mn. Dot 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 dot, everywhere dot dot. Okay, there's your coefficient matrix. Okay, your x vector is your variable vector, is what I call it, and this is usually written as a column matrix or a column vector: x sub 1, x sub 2, x sub 3, dot 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 that down to x sub n. Yuck. X sub n. Okay, because you have one variable. See, each of these coefficients corresponds to a variable. A11 to x1, A12 to x2, A13 to x3. The second entry here corresponds to what variable you're dealing with. Okay, that's why it goes up to n. Okay, and then finally your b vector is your, I call it the constant vector. That's what goes on the right hand side of the equation, and you have b sub 1, b sub 2, b sub 3. These are all constants, dot 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 down to b sub m. That's the m there because you have m equations, and there's one b for each equation. See, a11 x1 plus a12 x2 plus a13 x3 plus blah 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 plus a1 n x sub n is equal to b1. There's one b for every one of these. There are m equations. So that is your how we represent this equation. This represents the entire system of equations with that coefficient matrix, that variable vector, and that constant vector. Okay? Now, if you think of multiplying those together like I was just doing, let's just write down what they were. Remember, we are multiplying this row times this vector. Okay, so that gives you, and this produces a vector, and this may be a weird way to look at it, but it is indeed what it is. A11 x1, and that's supposed to be an A, but the A is not writing well. X1, A12 x2, these are pluses in between, plus A13 x sub 3. We're just going across here, this times this, plus this times that, plus this times that. That's what we're doing here. Plus, and then a dot, 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 plus a sub 1n times x sub n. Okay. Now, believe it or not, that is one entry. Okay, one entry in a vector. Okay. And the next entry in that vector would be a21 x sub 1 plus a22 x sub 2 plus a23 x sub 3 plus dot 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 plus a2n x sub n. Okay, that's the second entry. Third entry, just like you would expect, a 3, 1 x sub 1 plus a 3, 2 x sub 2 plus a 3, 3 x sub 3 plus dot 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 plus a 3 n x sub n. And then that next, you keep going down till the last entry would be a sub m1 x sub 1 plus a sub m2 x sub 2 plus a sub m3 x sub 3 plus dot 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 plus a sub m n x sub n. Okay, those are the m components that when you multiply this m by n matrix here by this n by 1 matrix here, you get an m by 1 matrix here. That's when you multiply this by that. A times x. Okay. Now what's that equal to is the b. Now I'm just, the book didn't write it out, but I could string those down and write them like that, or I'll just write them as the vector b. Okay. And the book writes the vectors bold. I have to put the arrow over it. Okay. Now if you think about that, notice that every one of these first entries here is an x sub 1, and that one x sub 1 is multiplied by all those. So we're going to take this and sort of rewrite it slightly to be, and they put the x sub 1 out front, x sub 1 times this column vector, a11, a21, a31, dot 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 down to a sub m. This drives me nuts. m1 plus x sub 2 times a sub 1 2, a sub 2 2, a sub 3 2, dot 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 down to a sub m 2. You get the idea. Plus x sub 3, and it goes on and on and on. Okay, so I'm running out of room. I'm going to hold this up in case you can't see your book at the same time you're looking at the close. Okay, that's what we've just done. Pulled out the x sub 1 from up here and made it a sum of those, and so it's still a sum, okay, adding a bunch of column vectors together with, and then you can rewrite this, and I'll try to rewrite that at the bottom, and that will be that your a sub x here, which is exactly this, the a times x, which is your right hand side here, left hand side here, and that's what this thing here represents, this whole matrix here, that can be represented as, and I'm going to come over here and make that x1 times some column vector a sub, just call it a sub 1. So this one is going to be a sub 1, and this is a heck. So just a sub 1, that's a vector. This will be a sub 2, that's a vector. Everything that the second element, and then you would have had an a sub 3 here for that vector, and you keep doing so. X sub 1 plus times a sub 1 plus x sub 2, these are the variables, times that column vector a sub 2 plus x sub 3 times the column vector a sub 3 plus dot 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 plus a sub n, x sub n, I should have done first, x sub n times the column vector a sub n. Okay. Now, and all that thing is equal to this column vector b. Okay? Now, what we say then, that this thing here, this represented here, we call that a linear combination. I don't know if I have room to write it, but I'm going to try to squeeze it in somewhere. Probably have the most room up here, but it's far from it. This is called a linear combination this pen is not doing well. Of column matrices, I'm going to abbreviate, column matrices, and that's A1, A2, A3, dot, 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 up to A, yuck! Column, comma, A sub n. Okay, those are your column matrices, and these are a linear combination of those. And now the funny thing is, the coefficients of that have become your variables. Okay, so what was your coefficients here forms a column matrix, and the coefficients of that are your variables. Okay, so things are sort of turned on their head a little bit, and I think I'm going to have to go to a clear screen to write the conclusion of this in here. Okay, and I can't figure out whether it'd be easier to type in most of this and write in what I can't type. Let me try that. I think that'll probably work a little bit better. So let's do some text in here. This is the box at the bottom of page 46. Okay, linear combination of column vectors. The matrix product AX, now I can't write the X bold, but that's a bold X, okay, is a linear combination of the column vectors, and this is supposed to be bold, A sub 1, and that's supposed to be a subscript. I can't subscript them. A sub 2, it's supposed to be a subscript. A sub 3, supposed to be a subscript. Dot, 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 down to and including A sub n. Well, my A didn't type. A, nope, it capitalized. A sub n. That's supposed to be a subscript. Okay? That form the coefficient matrix A. Okay. Now, I'm going to string this out here. Hopefully I got most of that spelled and written correctly. Okay. Now, here's what it turned out being, and this is what I was writing before, so I'll go back to writing it now. Okay, and I've got to get my pad here. This is like we had before, that you have the x sub 1 times a sub 1, a sub 2, a sub 3, dot, 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 down to a sub n, m. Well, actually, yuck! This thing, either right, so, okay, I should be having double subscripts here, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, down to m1, plus, that's your column matrix. This is what we were calling A1 before, column matrix A1, plus x sub 2, acting like a coefficient now where it was a variable, it still is a variable really, a sub 1, 2, a sub 2, 2, a sub 3, 2, dot, 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 down to a sub m2, and this we were calling a sub 2 before, okay, plus x sub 3 times a sub 1, 3, a sub 2, 3, a sub 3, 3, dot, 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 down to a sub m3, 3, and we'll plus dot, 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 this down to x sub n times a sub 1 n, a sub 2 n, a sub 3 n, dot, 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 down to a sub m n. This was what we're calling vector a sub 3, and this was vector a sub n. Okay. Furthermore, the system, I think I'll type this in again because it'll be easier for you to read and take up less room on the page. Okay. The system A x equal b, and the x and b should be bolded or overlined, is consistent if and only if b can be expressed as such a linear combination where the coefficients of the linear combination are a solution of the system. Sounds like a lot of weasel words to me. Okay. See if we can parse out what they really are meaning. Okay. The system that you got from this is consistent, meaning there is at least one solution. Okay. It's consistent if and only if that b, which this is equal to, I didn't write that in, but they didn't either, this b right here, can be expressed as such a linear combination as these are of the linear combinations. Whoa. There's a space there. Okay. The system that is consistent if and only if B can be expressed as such a linear combination where the coefficients of the linear combination are a solution to the system. These being the coefficients, and they will work when that is a solution. Now it seems like we're talking in circles there, and a lot of things with this linear algebra almost seem to be circular, but it's right. That is what's going on. So let's do example 7, and maybe we will see it making more sense. So I'm going to clear this unless there's questions about it. Any questions? Okay. So clear that, and let's do example 7. Here's a linear system. Got to get my pad back. Yuck. Okay. I've got to, I don't know how to undo that. Let me clear it. That will work. Okay. Now let's go back here. Okay. X sub 1 plus 2x sub 2 plus 3x sub 3 is equal to 0. 4x sub 1 plus, let me guess, 5x sub 2, let me guess, plus 6x sub 3 is equal to 3. 7x sub 1, they're really creative here, aren't they, plus 8x sub 2 plus 9x sub 3. Yuck! Why it does that, I don't know. X sub 3 is equal to 6. Okay, there's a system of equations. All right. Now, what they're saying is we can rewrite this to be x sub 1 times 1, 4, 7 plus x sub 2 times 2, 5, 8 plus x sub 3 times 3, 6, 9 equal to 036. Okay. All right. Now, I can't remember if we've done this particular thing again before, but what they're going to turn around and do is say use Gauss elimination on what we did back here. Okay, and let's just do that quickly. Let's do our Gauss elimination on the augmented matrix. 1, 2, 3, 0, 4, 4, 5, 6, 3, 7, 8, 9, 6. So we're going to have to do this is minus 4 times row 1 plus row 2. Too near the edge. Minus 4 row 1 plus row 2. I don't know if you can see that, but it's a pain in the neck came out there. Okay. Now, so this would become, leaving the first row alone, 1, 2, 3, 0. Let's do that. Minus 3 times 1, minus 4 times 1, Minus 4 plus 4 is 0. Minus 4 times 2 is minus 8. Plus 5 is minus 3. Minus 4 times 3 is minus 12. Plus 6 is minus 6. And that would be a 3. Okay. Minus 7 times row 1 plus row 3 is going to be the new row 3. So that's going to be a 0 here. Minus 7 times 1 is minus 7 plus 7, 0. That would be a minus 14 plus 8 is a minus 6. And minus 21 plus 9 is minus 12. And 6. Okay. Now I think you see, hopefully you see, the bottom row is exactly twice the top, the second row. This row is twice the second row. Okay, so this is a infinite number of solutions because that works. We haven't finished the problem, but the first thing I would do would be minus row 2 plus row 3 here, and this is not doing it sort of our standard way, but it still works. That would be a 0, and that would be a 0, and that would be a 0, and that would be a 0. Okay. Now that's not very standard, but we did it. Now what we're going to do is row 2 divided by minus 1, minus 3. Row 2 divided by minus 3, and that gives you a 0, 1, 2, minus 1. Okay, and I think we'll leave the top row alone. I don't think they say Gauss-Jordan, did they? They just say Gaussian elimination. Okay, so that's going to be, if I can find my pen, 1, 2, 3, 0. Okay, now we don't have a leading one for the third column, so that's going to be our t. So let x sub 3 equal t. Okay, our parameter. Okay, then the second row here says that x sub 2 plus 2t is equal to minus 1. So that says x sub 2 is equal to I like to do the t first. Minus 2t minus 1. If I could eliminate a minus sign, I would have done that. Sorry, I guess this cooler weather, I've now got a lot of drainage and my head is sort of closing up on me. I'm having trouble breathing, drainage and stuff like that. So there's x sub 2, and x sub 1 unfortunately is going to be a bear. X sub 1 plus 2 times x sub 2. So that's actually going to be, I'm going to do this all at once if it's okay with you. Okay, plus 2 times x sub 2, which would be this, that'd be minus 4t minus 2 plus 3t, because x of 3 is 3t is equal to 0. Equal sign isn't showing up well. Alright, so let's combine like terms there and say x of 1 minus t minus 2 is equal to 0. Minus 4t plus 3. Okay. And that says x of 1 is equal to t plus 2. Okay. So, our set of ordered triplets here would be t plus 2, comma, minus t minus 2t minus 1, comma, t. Now, they said if you let x of 3 be a minus 1. So let's do that. Minus 1. So this would be a minus 1 times a minus 2 would be a plus 2 minus 1 would be a 1. And if t was minus 1, this would be a 1. So they said that ordered triplet will work, and sure enough, that's the one they have. 1, 1, negative 1. And that works. Let's try it. Yeah, here. So 1 times this would be 1 plus 2 would be 3 minus 3 is 0. That works. 4 plus 5 is 9 minus 6, that would be 3. 7 plus 8 is 15 minus 9, that would be 6. Yes, that works. Infinite number of solutions there for your x1, x2, x3. Notice they have become your coefficients of these linear these vectors. Okay, now that is, B can be expressed as a linear combination of the columns of A, and that's what we did. They did these columns of your coefficient matrix. Where in the world is my pen? There it is. This was basically, just put a 1 in there. That's this. Here is that one, and here is that one. And this is a linear combination of those. Any numbers that'll work there, linear combination to give you that result. So all your solution matrices become the coefficients for that linear combination of column vectors. Now, there's that. And they seem like they go off and forget about it. They go through all this and then they really don't do too much with it yet. You'll probably see it again, but by the time you see it, you may have forgotten you saw it. Okay, but we'll get back to it later. Okay. Now they also say this: just as you partition A into columns and X into rows, it is often useful to consider an M by N matrix partitioned into smaller matrices that are not necessarily columns or rows. And they give this as an example, and where they get this I don't know, but it's perfectly legal. 1, 2, 0, 0, 3, 4, 0, 0, negative 1, negative 2, 2, 1, okay, and it says you can partition that, say, this way. Now I'm going to do like the book does and pick a light blue here and partition it like this. Here's a 2 by 2, there's a 2 by 2, 0 2 by 2 by the way, and here's a 1 by 2 and another 1 by 2. That's one way to partition. Another way you could partition, I'm going to erase that one if I can. Okay, so let's erase that. Yuck! It did it again. This kind of drives me nuts. I go to erase and it just gets rid of it. Okay. Now, you can partition this into a set of column vectors, not too dissimilar from what we just did. Here, here, and here, and call this column 1. We'll put an arrow over it. This column 2, we'll put an arrow over that. Column 3, we'll put an arrow over that. And column 4, we'll put an arrow over this. Now notice we're not adding those, we're just putting them together that way. And since we did that, we can put this, close it in as a matrix here, and that's the same matrix you have here. It's just this is a column vector here, just like 1, 3, -1, 2, 4, -2, 0, 0, 2, and 0, 0, 1. Those are vectors, so you come back to that. Or see if I can get my eraser back again. For some reason, sometimes the eraser acts like it gets tired and it doesn't want to work anymore. Okay. And that doesn't make any sense, but it sort of acts that way. Or you could split this into rows, partition it into rows, and call this row 1, because that's now a row vector. This is row 2. That's a row vector, and this is row 3. That's a row vector, okay? And you could then turn around and put this as a matrix, recognizing that each one of these row vectors represents that row, and you've got precisely the same matrix. So you can partition a whole bunch of ways, and again, they have you do this, and that's all we're going to do with it for quite a while. Okay. Now there is a blurb at the bottom of page 47, Linear Algebra Applied, and this sounds monstrous, but true. Many real-life applications of linear systems involved enormous numbers of equations and variables. For example, a flight crew scheduling problem for American Airlines required the manipulation of a matrix with 837 rows and more than 12,750,000 columns. That's a matrix. That is a huge matrix. To solve this application of linear programming, researchers partitioned the problem into smaller pieces, solved it on a computer, and got it done. Because to do that brute force, not going to happen. Okay? So anyway, if you want to follow up on that type of thing, there is a source listed there on page 47. That could be a paper topic. Hint, hint. I think I've received one paper so far in this class. There was a little issue with that, and we'll dealing with that separately, but rest of the folks, don't forget, you got to do a paper. Homework exercises here, either 1 or 3, they're both at Calc Chat, also answers in the back of the book. Any of the odds 5 through 9, they're all at Calc Chat. Either 11 or 13, all at Calc Chat. Any of the odds 15 to 27, they're all at Calc Chat. Any of the odds 29 to 35, they're all at Calc Chat. 37's at Calc Chat. Any of the odds 39 to 47 are at Calc Chat. Any of the odds are either 49 or 51 are at Calc Chat. 53's at Calc Chat. 55's at Calc Chat. 57's at Calc Chat. 59's at Calc Chat. 61's at Calc Chat. Either 63 or 65, both at Calc Chat. And this is beginning on page 48, and it'll go through page, I think it ends at 51. Yeah, ends at 51. Then any of the odds 67 through 81. Okay, they're all should be at Calc Chat. 83 should be at Calc Chat, and 85 should be at Calc Chat, and 87 should be at Calc Chat. All right, that was 2.1. Any questions on 2.1? Okay. 2.2, where 2.1 was operations with matrices, 2.2 are going to do the properties of those operations. We're going to look at some properties that are common to some of these operations. Okay? Now, I think okay. A little bit of verbiage first. This section begins to develop the algebra of matrices. What functions, what operations can we do with matrices, just like we did things with real numbers? Okay, actually, when you first started, you dealt with whole numbers. Then you can, or natural numbers and whole numbers. Later, integers. At some point, rational numbers. So, what you've done, what are some of the algebraic operations that you can do with matrices? And I'm sort of debating here. I think it might be good to type these. That'll certainly be easier for you to read. I'm not sure it'll be that much faster, but it'll be easier for you to read. So I'm going to clear that last thing that we just sort of talked on and then dropped it and ran on to something else. So clear that out of the way, and we're going to do text now. Okay, this is going to be a pretty massive text, so hang with me as I do it. These are the properties of matrix addition and scalar multiplication. So here's what you're given. If A, B, and C are M by N matrices, and C and D are scalars, then the following properties are true. If I can spell. Okay. First of these properties. If you do A plus B, add these two matrices together. They're both M by M matrices, remember? So you can add them. Okay? And that sum is going to be the same as if you did B plus A. That property is called the commutative property of addition. And maybe I should go on and put that in. Okay? May not have done enough, but let's try. That's the commutative property, of addition. Just like it was for numbers. Number two. How you group it doesn't matter. A plus grouping B plus C is the same as, oops, wrong symbol, oops, A plus B plus C. That is the associative property of addition. I like to say matrix addition, but they leave that out. This is 3. If you have those scalars, C times D, and multiply that by matrix A, you get the same result as if you did C times D times A. Okay. That is the it's an associative property of multiplication. Now, I have a little problem with that. Like I said, I've been wanting to say of matrix addition. If you say matrix multiplication, what comes to my mind is multiplying matrices together. We're not doing that. This is associative properties of 2 scalars with 1 matrix. I want to put that in there, but I can't type it all. The book didn't put it on, but it's not truly matrix multiplication. It's scalar multiplication, 2 scalars with 1 matrix multiplied together. And that certainly is true. Okay. The fourth one of these, well, that's supposed to be a period. They're supposed to be backspaces. Okay. Is 1 times A is equal to A. Now that's simply the multiplicative identity. That 1 is the multiplicative identity. These will make more sense when I spread them out a little bit. Number 5. C, scalar C, times the sum of A plus B is equal to, my stomach is making a lot of noise. I hope it's not being picked up here. C times A plus C times B. That's just the distributive property they just call it that. I don't want to type it in, but I want to say this. This is the distributive property of scalar multiplication over vector matrix addition. Just to say distributive property without saying what kind is a little bit misleading in my mind. And here's number 6, last one, but we're going to spread them out some. If you have C, scalar C plus scalar D multiplied by vector A, matrix A, that gives you CA plus DA. All right, and that's another distributive property. Now that would be, for me, scalar multiplication over, vector multiplication over scalar addition. Okay, that's how I would express that. Okay, it's also a distributive property. Now let's see if stringing these out will make them look a little better. Okay. That was an if there, not an it. If A, B, and C are m by n matrices, meaning all the same size, C and D are any old scalars in the world, then the following properties are true. A plus B is the same as B plus A. And that is a commutative property of matrix addition. And then the associative property is here. This would be an associative property of two scalars in one matrix. Okay, I just can't stand to just leave that without some sort of definition. Multiplicative identity, the number 1 multiplied by any matrix gives you the same matrix. Okay, just like the number 1 is the multiplicative identity element in real numbers as well. And then these two distributive properties, one is distributing scalars across the sum of two vectors, the other is a vector across the sum of two scalars. Okay, now they go into a little proof here of a couple of these. Let's see what difference it makes. How do we use these? Okay, and I think let's go on to clear the page here, and we will do example 1. Okay, we got about 6 minutes. Okay, so here's example 1. This time I'm going to go to my draw mechanism here. Okay, what if we had these 4 matrices? Oh wait, I don't want to draw with my finger, I want to use my pad and pen. So here we have it. Let's go back to black. Okay, column vector or column matrix 1, 2, add to that column matrix, column vector minus 1, minus 1, add to that, and these are all the same size so you can add them, 0, 1, add to that 2, negative 3. Can you do that? Of course you can, because they are all the same size 2 by 1 column vectors or column matrices, and all you do is add them in whichever order makes the most sense. So for the first one here, I'll do 1 minus 1 is 0 plus 0 is 0, so that gives us a 2 here. Okay, down here the 1 minus 1 and plus 1 are going to give us a 0, 2 and negative 3 will give us a minus 1. So any way you want to add them, that's what it comes up to be. Okay, pretty straightforward and hopefully pretty simple. Now, one important property of the addition of real numbers is that the number 0 is the additive identity element. And what we mean by that is any real number C added to the number 0 is always going to give us the real number C. No question about it. 0 is the additive identity element, just like 1 is the multiplicative identity element. It doesn't change what you're doing. Okay? For matrices, there is a similar property, specifically if A is an m by n, okay, matrix, then there is this other matrix called the 0 matrix. Now I put it that way to keep you from thinking it's an O. The 0 matrix, and this 0 matrix is also an m by n. We don't put the time sign in it, we just call it mn. Okay, that's the 0 matrix, and what it means is it's an m by n matrix. Every element in it is a 0. N zeros in m rows. Okay, that's the 0 matrix, and that becomes the additive identity element. Boy, this is all lousy writing. identity. It works better if I write longhand, but it's harder to read. For the set of all m by n matrices. So whatever m by n matrix you have, A, m by n, if you take A and add it to the 0 matrix that is also an m by n, you're always going to get A. But A has to be the same size as the 0 matrix. Okay. Here they give the example of A 0, 2, 3 would be 2 rows, 3 columns, 0, 0, 0, 0, 0, 0. Very exciting matrix, right? All right. Now, when they usually write it, and I can't tell if they meant that to be a 0 or not, but they write it bold, so the only way I can do it is do that. Now, it's not a vector, but that just means it's bolded. Okay. Now, we have some properties of the 0 matrices. I don't know if I'm going to have time to type those out. We've only got 2 minutes left. So why don't we pause right there, and we'll start next time with theorem 2.2. Let me make sure I don't have another mark on the page. Okay, and let me give you some homework exercises, not many, but just a few homework exercises in 2.2. Okay, hopefully we'll pick up speed a little bit here now, but matrices take a long time to do. I think you can do any of the odds 1 through 5. Okay, they all should be at Calc Chat. I think you can do all the odds 7 through 11. They should all be at Calc Chat. And maybe let's hold off on 13, and we'll do those a little bit later. All right. I'm cheating you out of a minute of your tuition dollar here, but let's see, are there any questions, issues, concerns, anything else to be brought up before we call it quits for today? Anything? All right, the first thing I'm going to do then, if there's no questions or issues, I'm going to stop sharing. I'm sick and tired of sharing. And unless there's something else, let's end the meeting. Any other comments, things before we go? All right, so we'll end the meeting there. We'll see you on, well, I'll see all of you tomorrow, twice, and then we'll see you again on Thursday. Okay, so take care. Be safe. Bye-bye.